If everyone could mute their microphones, that'd be great, just so we don't get any sort of background noise or feedback. The talk will be recorded, but we'll stop the recording for questions at the end. So if you have a question, you can also, we'll keep an eye on the chat. So if you want to put any questions in the chat, we can ask those for you. Yeah, so our first speaker today is Marcello Bernardara, and he's going to tell us about Fanos of K3 type, isomorphisms, classification of Hodge structures in K3 categories.
Okay, thank you very much. So I start sharing my whiteboard, and here we go. So this is there is already a hello I wrote before, just to check that everything works. So this is work with this joint. Okay, now it should work. Is joined with Enrico Fatigenti, Laurent Manivelle, and for the last part that we are working out now, and I will tell you about in the second part of the talk, and there will be the contribution of Fabio Tanturi as well. So let me start with some definitions, vague definitions and motivations. So this first part is just to tell you why do we care about this problem of classifying Hodge structures and K3 categories into as subcategories or sub-Hodge structures of Fano varieties. So the idea, so just let me be very starting from the very base. I work over complex numbers, and for me X, I will say the X is Fano. If it's Moods projective, I will not consider singular cases today, or non-projective cases over the complex numbers, and I ask the anticanonical bundle to be ample. So this is automatically gives automatically projectivity of your variety, but anyway. And the other, this is a very interesting family of varieties which are, we know that in every dimension there is a finite number of deformation classes of such varieties, and they are classified up to dimension 3, and some known examples are known in every dimension. And on the other hand, there is another class of varieties that is very important in modern algebraic geometry, is hyperkähler variety. I will use the M to denote it, and then let me be sloppy here. I just consider the projective case. Okay, so I ask this variety to be smooth and projective. So in this talk, always complex, and then I ask the canonical bundle to be trivial, the variety to be simply connected, and then I ask that there exists a two-form omega, holomorphic two-form omega generating H to 0, so that the sections of the global two forms are generated up to scalar multiplication by this omega. Okay, so these are standard definitions, and with respect to Fano varieties, the problem with hyperkähler manifold is that there are very few hyperkähler manifold which are known. There are only a few examples. And known for M. On one hand, the Fano varieties we know that are bounded by, for every dimension, the number is bounded. There is no such result for hyperkähler variety. There is some bound on Bethe numbers or this kind of numerology, but there is nothing very specific about the finiteness of these kind of examples. And technical, I mean, there are, if you want, only 4 examples, and which are most of them. Let me be again sloppy because I don't speak about hyperkähler variety later is just to justify why do we care about Fano of type K3, and most of them arising from K3 surfaces as moduli spaces, or the formation of moduli spaces of K3 surfaces. Okay, this is where, so there is this famous result by Mukai, for example, that says that if S is a K3 surface, then you take some Mukai vector V, somehow good in some sense. Okay, you want the modular space to be non-empty and non-singular. Then you have that the modular space of stable sheaves, vector bundles on S with this Mukai vector is a hyperkähler variety. Whose dimension depends on V of some dimension, of some even dimension, depending on the properties of V. So this is, if you want, some of the main example. Then this very specific example are Hilbert schemes of points where the vector is given as the vector of the Chern character of a point of a zero-dimensional subscheme of a K3 surface. But okay, so the idea is, if we want to construct hyperkähler varieties, then what has been done for a long time is to use the, of course, K3 surfaces are hyperkähler if you look to this definition in dimension 2. And then what has been done for a long time has been to study modular spaces on K3 surfaces, and also one of the famous O'Grady's example of the sporadic case, which is not of this type, is the resolution of singularities of this kind of variety. But let me be very, very just general here, because it's exactly something that I need for the aim of this project, and will be not a part of the project. It's just to say that if we want somehow hyperkähler variety, we need something that looks like a K3 surface. And here is where Fano varieties enter the play. And let me say when a Fano variety is of type K3, and let me again give a very vague definition. Let me start with Hodge structure. I mean, the definition is a bit vague because we have a lot of examples, and then we try to adapt the good definition and to understand whether this K3 structure inside the cohomology of Fano variety is well defined or not. So let me say something which is not a definition that is only practical for this talk, in order not to write down 20 times the same thing, but it's not a standard definition. I would say that the Hodge structure V, say integral Hodge structure, I would say that is of K3 type, and I will give a very weak definition of this property. If it has level 2, weight 2, sorry. And if we have that the complex 2-0 part of this weight 2 Hodge structure is one dimensional. Okay, so this is completely non-standard. If you want, the Hodge structure of a K3 surface has much more properties. We know completely the lattice with respect to the intersection form for a K3 surface, which is a much stronger definition of this kind of Hodge, of the Hodge structure. It will be a much stronger definition, but in my case, I want to have a flexible definition for this type of Hodge structures that I want to see inside the Hodge diamond of Fano varieties. So this is just, if you want, a working definition for this seminar. Okay. So in the next page, I will tell you about.
So an abelian surface is also of K3.
Yes. But you will see why, because we have as soon as I will define a Fano variety of K3 type, what we are able to do on all of the examples that we have and that I will tell you about towards the end of the talk, is to have the numerical data of the Hodge diamond and check whether the Hodge diamond contains these kind of Hodge structures in middle cohomology or in other cohomologies. So an abelian surfaces for example, is also. I don't ask, for example, so far for V11 to be big, to be at least 20-dimensional, but we always the case of our examples. Okay. It's just really a working definition for the next definition that I'm giving. So which is a bit more important and more relevant to this talk. I will say that a Fano variety X is of K3 type if the cohomologies for every j, so x from 0 to twice the dimension of x, we have that the jth cohomology of singular cohomology of x is either weight 0 or is of K3 type, as I defined earlier. Okay, we have, of course, stronger notions where we ask actually this the Hodge isometry or for some kind of non-primitive sublattice or something on the transcendental lattice. This is, of course, very interesting and very important, but let me so far focus on this very simple down-to-earth definition.
When you say weight 0, do you mean level 0?
Yes, level, sorry. So, yes. Of course. So this is the kind of thing that we can detect using computer algebra for all the examples of the fourfolds we can produce that I will talk about later is this kind of shape of the Hodge diamond. So either you have Hodge, the cohomology which is concentrated in the central column of the Hodge diamond, or you have something which is of K3 type. So you have one, a big number, and then again one. Okay. And let me just give also the non-commutative definition. So in the non-commutative word, we say that a geometric DG category. So by geometric, I mean that it can be embedded in some derived category of some, I will tell you, DG category A. So geometric means that there exists a fully faithful embedding, fully faithful functor A into some dBy for y smooth and projective. So this DG category is of K3 type or 2 Calabi-Yau. If it has a Serre-functor, so the Serre-functor is automatically inherited by this embedding as admissible subcategories of derived categories of smooth projective variety can be endowed with the Serre-functor induced by this by the projection. And if the Serre-functor of A is nothing but the shift by 2. So as much as the definition for the Hodge structures, this is a weak definition in the sense that, as Sasha asked before, also abelian surfaces have the derived category of an abelian surface will be of K3 type. Okay, so we just ask to be somehow, we mimic somehow the fact that the canonical bundle is trivial and the dimension is 2. And then this will let us define the non-commutative version of the definition above. I will say that the Fano variety is of derived K3 type. if there exists, so the Fano variety X, of course, if there exists a semi-orthogonal decomposition of the bounded derived category of X by some finite set of DG categories and another finite set of objects that I will tell you in 1 second. So we want this first category to be of K3 type, and these objects to be exceptional objects. So somehow you see that the parallel between the Hodge structure and the category. So we have either something that looks very weakly like a K3, like some Hodge structure of a K3, and we have something that looks vaguely like the Hodge structure of the derived category of a K3, and something of level 0, and here something exceptional. So it's something that is, if you want, the Hodge structure of a point and the Hodge of finite number of points, and here also the derived category of points. Okay, so these are very, very vague definitions. We see in the examples that I need to stay vague in order to produce a lot of examples and ask questions also about how to make these definitions more precise. What does it mean to classify this kind of varieties and categories and so on. So let me just to remind a little bit the very first the motivation. So the hyperkähler, the definition of hyperkähler and the fact and why hyperkähler relates to this problem. Let me just start by giving examples, very basic ones. So example number 0, which is not really an example of Fanos of K3 type. So example 0 is not a Fano, but is of K3 type, and you can guess it's just a K3 surface. So a K3 surface has, of course, such a decomposition, and there's, of course, such a Hodge structure. And I will keep this example 0 because somehow, if you want, we will have Fano. You can produce, for example, Fano varieties where the derived category is decomposed by categories of K3 type and exceptional objects, and the categories of K3 type are derived categories of K3 surfaces. So somehow in the classification, for example, of this kind of Fano varieties of derived K3 type and their subcategories, I want this example to be there. So the most well-known example probably surely is the one of cubic fourfolds. So I will take X inside P5 to be, let me introduce also a notation. So we will study subvarieties in Grassmannians or product of Grassmannians that are defined by the 0 of a general section of a vector bundle. So here a cubic fourfold is such an example if you want. This is the 0 locus of a section of a general section, of course, because I want it to be smooth, as I asked this in the definition of O3 in P5. And so this is the Hodge structure is just a calculation for, if you want to check that this is a K3 type for the Hodge definition. This is just a simple calculation. And then if you want to go deeper, as Sasha asked, there is a very, very, very strong relation between these fourfolds and K3 surfaces that is being described by Hassett and many other people. But the derived counterpart is due to Sasha, and I just is of derived K3 type, and then there are sorry, these shouldn't be parentheses. Up. Okay. and there are many people that related the fact that this is very well known. This is a very huge topic in algebraic geometry, with the questions about rationalities of these fourfolds, the question about the existence of a K3 surface that actually represents this category, or the Hodge, the non-primitive Hodge structure of this Hodge in the H4, and all of these topics are also related to what I mentioned in the introduction as a motivation. Also, we can construct hyperkähler varieties from X, from such X. Oops. X as moduli spaces. For example, the most well-known example is the Fano variety of lines, which is a 4-dimensional hyperkähler variety. But still, these are deformation equivalent to moduli of K3 surfaces. So they don't exactly give a new example. They give an example where a family is complete, but it's still deformation equivalent to a known example. So this is the very well-known example, and we have two other 4-dimensional examples. So let me introduce them. So of course you see that a Fano variety of K3 type, if you look to the definition, we need the dimension to be at least 4, because of course Fano variety has a Hodge diamond to Hodge diamond. So as I0 equal 0 for every positive I, so your Hodge diamond is squeezed inside this hull, if you want. And so 4-dimensional examples are the smallest purely Fano examples. Of course, if you go to dimension 2, there's no Fano anymore. And the next example is another 4-fold example, which is Gushel-Mukai 4-fold. Here, X is in G25, and X is the 0 of a general section. I will write only 0, not to write down every time, but every time the same thing, but is exactly what I meant before, is the 0 of a general section of, so it's a hyperplane and a quadric inside this 6-dimensional variety. So you cut with the hyperplane and the quadric, generic ones. And you get this 4-fold, which is so smooth, and of K3, and of derived K3 type, is both of K3. This is the work is of DK3 and Hodge K3, if you want, type. And again, there is a semi-orthogonal decomposition as we want. I will not, and here also this semi-orthogonal decomposition and this structure that you can obtain are very closely related to rationality of this, conjecturally to rationality of these 4-folds, exactly in the same way as with the same circle of ideas that gives the conjectures on the for the cubic 4-fold. And the last known case for 4-folds, it's a more exotic case, which is described by Kuchle, and it's called C5 in this list. So Kuchle has this list of all possible Fano varieties that are sections of line bundles of the zeros of section of vector bundles on single Grassmannian of dimension 4, and the 4-fold C5 in this case is a variety which is defined inside G37, so in the Grassmannian of 3-dimensional subspaces of a 7-dimensional space, and is the 0 of so Q star 1. So Q is the quotient, so is something of rank 4. And then you want U of 1. So this is the tautological, so it has a rank 3. And then you take a hyperplane section, so you take O of 1. So if you, for example, you can study the 5-fold given by this and then take a hyperplane section. So you can also check that the dimension is fine because this is of dimension 12, and then you cut with a 7-dimensional bundle. Yes. No. 4, 3. Okay. Yes. And so this is a bit more mysterious because we know that is of K3 type from the Hodge point of view, but as far as I know, not known whether it is of derived K3 type. So there is some work of Sasha for the 5-fold, but still this semi-orthogonal decomposition is not known, at least to me. So if you know some reference I would not be aware of, I'm happy to learn. So this is these are the example for 4-folds, and somehow I will give them to you because now I give some higher dimensional examples for just to state the theorems we proved. And but the work in progress that we have with Enrico Fatigenti, Laurent Manivelle, and Fabio Tanturi is aimed to say that these are the only possible up to, I mean, only possible K3 4-folds of K3 type up to birational transformation, so up to blowing up, blowing down, and but the Hodge structure and the category and the K3 categories that you can find inside 4-folds should be already all listed. So we have a lot of examples. We are not able yet, with some idea, we are not able yet to tell that they're all of them. I will give a more precise statement later. But this is the reason why I list all of these examples. And now let me give some higher dimensional example. The first one is studied by Debar and Voisin in their paper, also with the aim of constructing some hyperkähler variety as a modular space over it. So this is called the Debar-Voisin construction. So the Debar-Voisin is more the name for the hyperkähler variety associated to this Fano of K3 type, but we have X sitting in the Grassmannian of 310. So the dimension is much bigger than the previous cases. This is just a hyperplane section, so it's just the zero of a general section of one. Okay, so it's 20-dimensional, and it is of Hodge K3 and derived K3 type. This second part is due to Sasha. So there exists the semi-orthogonal decomposition that we require and the Hodge structure that we require. So we really have this diamond. And actually, I didn't tell you, but with respect to the question that was raised when I gave this very weak definition of K3 type Hodge structures, these are structures that we have really look like the one of the K3 category. So there is something that has Hodge numbers 121 somewhere. So it's really not such a weak result as the definition may suggest. And then there are other examples that have been studied a bit later. So the next is Leff and Manivelle that are quite similar to this one. And I will give this presentation. You are in G3-9 now. And now you take the zero, not only of O1. So you don't take only an hyperplane section, but you take a hyperplane section of the zero locus of this bundle. So if you want, you can see X inside the symplectic Grassmannian 3-9 as a hyperplane section, because because here you take a general section of this is just a two-form omega. So V9 is the space where you define where you look for your three spaces, and the zero locus is where this form is degenerate. So it's what we call the symplectic Grassmannian. And so this is, if you can calculate the dimension, is 14-dimensional, and is Hodge K3, but we don't know if it's derived K3 type. We have conjectures that I will tell you about. And again, you can repeat if you want this game, and this is exactly the way we started our study. This is an example which I read for the first time in a paper of Fatigenti and Mongardi. So you take X in G38 now, and X is the zero of, you always take a hyperplane section, and then you take not only one two form, but you take two of them. So you take this bundle twice. So somehow is the hyperplane section of a double symplectic Grassmannian. I will not write this again. So you have the locus of three planes that are symplectic with respect to two forms, and then you take the hyperplane section of this variety. And this is 8-dimensional, and is of H Hodge K3 type, and still the derived question is open. Let me just tell in very, just to be a bit suggestive, we don't have any result in this direction. We put this in some phantom color. We can go further. We can take X. So this is not an example. We can take X in G37 and to be the zero of, so the hyperplane section of a three symplectic Grassmannian. So you take the zero of three copies of this bundle of, the zero of three generic section of this bundle, and then you take hyperplane section. This is due to Mukai. This is a K3 surface. Somehow this process ends up on a K3 surface of Getty, lowering the dimension of the ambient space if you want, still taking three planes and taking one more two forms. I just tell you this because maybe later, if I have time to explain how we get. So I spoil a little bit. This example are the same example with respect to the fact that they have all the same Hodge structure, the Hodge structure that appear, and conjecturally the categories that they should appear are the same actually. So they can be considered to be the same example. And last but not the least, the last two examples are even more interesting because they are. If you notice the definition I gave, I don't ask for a single Hodge structure of for a single Hodge for a single cohomology to carry a Hodge structure of K3 type, and this is the case for all of these cases that I presented up to here. Example 1 to 6 only have the K3 Hodge structure in the middle cohomology, but the other cohomologies are of level 0. And here we have cases where we have more than one Hodge structure of K3 type in the cohomology. So this is another example from the same paper as example 6. So we are in G210 here, and X, I guess, can be seen as the zero of Q star 1. But if you want a more explicit description, sorry, X is the set of planes in some 10-dimensional space where you do your Grassmannian here. So you fix. Okay, let me write it this way. You take a three-form omega on V10. I will write you just 1 second for given omega in wedge 3 of V10 dual, so a three-form on this space. You look for planes in this space that are where this omega is trivial. So you restrict omega to this point. Okay, P1 and P2 belong, of course, to P. So you want planes where this tree form is degenerate. So this is 8-dimensional and has H10, H8, and H6 of K3 type. Sorry, I try to squeeze everything in the same in one single page. So this is interesting because you see why I gave such a light definition, because we classifying and trying to calculate with the help of computer algebra, trying to calculate new examples. We have these kind of things popping out, which were mysterious before we actually found a way to explain it, but which are more exotic than the other ones, or just special in some way. And the last example is due to Peskin. So there is a variety which is called the Peskin variety, is in X. Sorry. In let me, if you want, I would. Okay, I write P9, but you can think of P9 as G110. So there is some a 10-dimensional vector space around where you take lines to build your P9. And this variety is not the zero locus of a general section of a vector bundle. You cannot describe it this way. It's still a Fano variety, but you can define in a very similar fashion to the previous one. It's a set of lines in V10. In the V10, you're taking the lines to build your projective space, where again you fixed the tree form omega, capital omega on this V10, and then you want this form, these two form to drop rank. So in here V is in the line L. Drops rank means that in general this two form is a two form on a 10-dimensional vector space. This Q2 form on a 10-dimensional vector space will have rank. So it's symmetric, it's anti-symmetric. So I will say something wrong probably, but so here you take the locus of lines where these two form as rank non-maximal rank, and
We
this
can't
is
see the bottom line.
Sorry.
We can't see the bottom line.
Oh, sorry. So I give the example in a new page then. Sorry. So you don't see the example 8 at all.
I don't see the bottom line, drops rank. I can read drops rank, but I can't read what's under there.
Okay, for every V in L, so let me write it next. So I don't go so as deep as in the okay, for V in L. So V, I take V in the line L. I mean, this notion is well defined up to scalar multiplication. So you want the vectors where this omega drops when you put the vector in the first place, then this becomes a two form that drops rank. And this is 6-dimensional smooth Fano variety of index 3 if you want, and also has a very similar behavior to the previous one. It has H8, H6, and H4 of K3 type. I hope you can read the whole of it. Can you? Okay, so this is a long list of examples. I hope you're not getting bored. It's over because actually this is actually the content of our work. Somehow these examples, these higher dimensional examples from 4 to 8 are all the same example. So this is the theorem we could prove with Enrico and Laurent. almost now 2 years ago. And so the sloppy version is examples 4 to 8 are the same. What does it mean? It means that if we fix a 3-form omega on a 10-dimensional vector space, on a 10-dimensional vector space, then we can take x omega in G310 to be a hyperplane section, the hyperplane section associated to this omega. Section of O of 1, but O of 1 you can see it as wedge 3 of U star, right? Okay, then for the same, let me just change the names. You can take, okay, let me use it's not easy to keep the notation. So this is the associated, these two are the associated varieties as in examples 7 and 8. Respectively, okay, so the locus of planes where the ranks drop for this 3-form, and the locus of lines, the locus of planes where the 3-form is trivial, and the locus of lines where the rank drops. And then what's the construction for the other cases is the following. So we can I make it here so we can define this. If we fix a 1-dimensional subspace of V10, and I call V9 the quotient, then I can write this capital omega as omega prime plus the vector generating, the dual of the vector generating V1 wedge 2-form omega 1 prime with this a 3-form on V9, and this a 2-form on V9. And so here, with these notations, I will have some y omega prime. So the choice depends on the omega I fixed before, and also on the choice of this line. This will be something that live in G210. So this is as an example, I guess it was 5. And then the last thing you want to do is to go to some z, because sorry, not to 10, 3, sorry, 3, 9. I was surprised by this thing. So because still omega prime is a 3-form, so we'll give you a hyperplane section, and small omega prime is the 2-form, the symplectic. We take the symplectic planes with respect to this, 3 planes with respect to this form, and then we'll have some omega second, small omega second, small omega 1 second. If you want, the idea is that now to take V1 in V9, but we have to be very careful to this choice, call V8 the quotient, and make the same construction. So write omega prime as omega second plus so V1 prime, sorry, the notations are horrible. E1 prime dual wedge omega 1 second, and omega second is just the restriction of omega prime to V29. Okay, and so here we have to be careful, because if you want this locus to be not to be singular, we want V1 prime to be actually the kernel of, I mean, the projection and everything to work. We want this to be the kernel of omega prime. Okay, so, and this is in G38 as in example 6. Okay, so we can make a construction. You fix the tree form, so you fix the isomorphism class of your hyperplane section of G310, and then you produce all of these varieties just by the only choice you are left with is this choice of V1 in V10, because V1 prime is fixed by this condition. And then the claim, the actual claim, what does it mean that these examples are the same, is that all the K3, there is a Hodge isomorphism. So if I denote by K inside H20 of X omega Z, the minimal Hodge structures, sub-Hodge structure containing up to tensoring with C H 1921. Sorry, 911. What am I writing here? So if you want, this mimics the transcendental lattice for the K3 surface. And then if you do the same for all the others, so if you look for the minimal Hodge structure containing containing the K3, I mean the minimal K3 structure, transcendental K3 structure, if you want, then K in H. So Y is 14-dimensional. You have Z that is 8-dimensional. Sorry, the notations are really horrible. And then you have more K3 structures in T and P. So this is H, J, T omega Z. So J here is 6, 8, or 10. And also for P, J here is 4, 6 of 8. Have the same property. Let me, if you understand what I mean, meaning that they are the smallest, the minimal Hodge, indecomposable Hodge structure containing the weight 2. I mean the part which is responsible for the non-trivial weight 2 for this K3 structure. And conjecturally, we have semi-orthogonal decompositions for all of these varieties. So we know the semi-orthogonal decomposition for this one, given by exceptional objects and 1 or 3 copies of the K3 category of dB X omega, so the one which was described by Sasha. So conjecturally is because we have the functors, we have everything, we have the correspondences that put in relation the categories of these varieties, but you have to mutate hundreds of exceptional objects, and we are not able to do it by hand. So to check the compatibility of these functors, but actually you can see this statement as saying, as in a very complicated from the notational point of view way, that all of these examples are one example, and somehow is disappointing if you want with respect to the construction of new moduli spaces or other example of hyperkähler varieties, because what he's saying is that you can, if the K3 structures are the same and the categories are the same, you cannot construct new examples of or families of hyperker varieties out of this, even if they are deformation of Hilbert skips. There, as soon as you do it in X, so in the hyperplane section of G310, then you do it. You do whatever construction you do. You use these correspondences and you reproduce it on the other varieties, and vice versa. And a similar the last 5-10 minutes, I will tell you about some work in progress, which takes a lot of time. And this is where Fabio Tanturi joined the project. So let me give this claim. Let me just mimic the claim we had before, but in the case of fourfold. So if let me write it in some fancy way, which is similar to the theorem I wrote you before. Every Fano fourfold of K3 type or derived K3 type is the same in the same sense that I told you before. So this as the same Hodge structure or as the same derived category K3 subcategory up to exceptional object as examples. Now I have to include 0, which is not a Fano fourfold, but it means that there is a blow up of a K3 at some point from some projective space or from some Grassmannian, also from some Fano with the central Hodge diamond. And then 1, 2, 3. So why do we give this claim? And so the idea is that you can relate all the Fano fourfold of K3 type to via some correspondence, and in general it will be some irrational correspondence to one of these 3 examples, either to one of these 3 examples that are really Fano fourfold, or blowing up some K3 surface in some Fano fourfold, which is just which is just a central Hodge diamond, like blowing up a K3 surface in P4. If the result is Fano, of course, is a Fano fourfold, which is not related to 1, 2, 3 in general, unless maybe it's okay. So this is really a very fancy claim, and now I tell you what is true. What we know to be true is that the fact is that we can produce I guess the last, I checked the file yesterday, 66 examples as zeros, 66 different examples, as zeros of bundles of sections of bundles in either product of Grassmannians or flag varieties, product of flag varieties. Let me write it like this. And we have explicit. So this is done with computer algebra. So we have a way to just plug in. You put the ambient space, you put the platism of the bundle you want to take sections of, and you run the computer, and you run some computer algebra, and you get the Hodge diamond of your fourfold. And then we went up to codimension 20, if I'm not wrong. And then the calculations become longer and longer. And this is that there are a lot of examples that appear many times, because they are just different identification of ways of describing the same variety. And then we can go down to 66 different examples, and we have an explicit description of each of them. all of them, of course, are of index 2, of index 1, because the index 2 cases, index 2, 3, 4 are already classified. 2, 3, 4, 5 are already known for folds. And each one is related by some blow up or some blow down or some birational correspondence to something where either a cubic fourfold or a Gushel-Mukai variety or a rational variety with central Hodge diamond. The Kuchle does not appear anywhere. It's really an isolated case, which is still quite unknown. So we don't have examples related to the third case. And actually, so this is for the K3 type. We can also so these 66 examples are taken from a database of about 900 Fano fourfolds obtained the same way. And the huge guess, and we were a bit more optimistic a couple of months ago, is that we can give the list of all the possible Fano fourfolds obtained in this way, and we are working on this. Are they all? The answer is no, but
Are they all what?
or all the possible Fano fourfolds of index 1. Are all Fano fourfolds of index 1 in this list? Thank you, Sasha. It was very sloppy. So the answer is no up to some, but maybe, so the only abstraction we not, but maybe almost. So things are a bit confusing because it's a very, so this way we obtain Fano fourfolds is numerical. So you just plug in your flag variety, you tell the computer to move some numerology of the pletism of your bundles, check whether the variety is Fano is a purely numerical operation for the computer. So what it checks is that whether the restriction by adjunction of the canonical bundle of you write the Picard group of your ambient variety, you restrict the canonical bundle to your 0 of some of the vector bundles you fixed, and you checked if the numbers stay negative. So not all of those. You can have cases where these numbers one of these numbers go positive or 0, and still you get a Fano fourfold. For example, in the case of threefolds, there is this paper by Fatigenti, Tanturri, and De Biase where they show that I guess 80 something over the 105 Fano varieties known can be described in this way. So this is the upshot to show that when you so the idea is.
Are you making any assertion that these guys have K3-like structure?
No, the K3-like are the 66 examples. So these 900 are all the Fano fourfolds that we can produce. Most of them have central Hodge diamond or curve-like Hodge structure.
You're conjecturing that the number of Fano fourfolds is less than 2,000.
So we conjecture that the number of fourfolds is less than 2,000. I don't know. We have this.
You say you have almost all of them. Nobody has any idea how many Fano fourfolds there are.
No, that's we don't have any idea. There is some. So the fact that we have this database, and then we went up to codimension 20 with our computation. Somehow it's funny because there is one Fano one fold, there are 10 Fano two folds, there are about 100 Fano threefold. So somehow it's a stupid guess. It's a very stupid guess to say that 1000 can be a good guess for the Fano fourfolds, but it's really, in fact, what we think is that we cannot produce more than that, and the computer cannot tell us more than that, because the calculations are tougher and tougher. And the problem is that there are infinite series that you can produce. For example, if you take a Grassmannian and you take any Grassmannian and you take the zero of the general section of the tautological bundle, then you get just the smaller Grassmannian. So this is the most difficult thing, is to say there is a huge list of identifications of if you fix some special vector bundle on some product of Grassmannian, so you want to say that that you are just producing a smaller Grassmannian or a smaller product of Grassmannians. So this is the most difficult thing, because when the numerology of your bundles, maybe if the first Chunk class, for example, of the bundle is big enough, then you can bound somehow the codimension of your Fano if you want it to be a fourfold. And we know that rank 20 can, for most of the bundles you can think a bundle of, for most of the bundles you can take on product of Grassmannians, for example, you can say that you can bound the rank of your bundle to be 20 if you want to have a Fano fourfold as a result, purely numerically. But then there are bundles you cannot control. For example, on the product Grassmannian, you can take on one side you take the tautological, and on the other side you take the quotient, and this gives an infinite list of examples, because the C1 is very small. It decreases the negativity of your canonical bundle very slowly, but all the examples that are produced are somehow identified with previous one, but we don't have an algorithm to kick out all of them. So this is the kind of problems we are facing, and we are trying to understand. But still, we have these 900 Fano fourfolds, which are all different from each other. We are able to make the difference, firstly numerical, just very simply, and then you check the things that are numerically equivalent, and with the same numerology, and then you try to understand if they are isomorphic or not. And in this database, the rank of the codimension of this fourfold in the ambient space is very big, so that beyond this, the computer cannot do any computation so far. And we know that this bound is fine for most of the bundles, for a lot of bundles, but there are still a lot of cases we cannot manage. Infinite series we cannot manage. And in this 900, in this database of 900 Fanos, we found 66 examples of fourfolds which are of K3 type, which have the Hodge diamond of the shape one wants. So with this level 2 Hodge structure in the middle cohomology, and we studied all of them one by one. And sorry, maybe so the time is over. So maybe you have other questions, but maybe I can give you a couple of examples. Some of them are stupid. For example, or known. For example, if you blow up a Pfaffian cubic along the del pezzo of degree 5, then of course you get the blow up of P4 along some surface which is birational to a K3. You just have to check that this is Fano, and some of them are more exotic. So we are trying to write them, all of them, clearly to share this with the community, because we think that there are a lot of interesting cases that can let people understand this kind of problem better. So I think I know I should stop here, but please, if you have questions. Thank you.
Can I ask you about the claim?
Yes.
So what about Vera fourfolds?
Vera fourfolds. Did we miss this in the list? How are they defined? Sorry, forget
So
yes.
the double covers of P2 times P2 branched over divisor of type 2,
Yes.
they are of K3 type.
Yes. Do you know if they can be seen as a zero of a vector bundle in some homogeneous space?
No idea.
So this is maybe why I forgot to put them in the list. Okay, so you're right. Sorry, we could, all of us. I don't know. Maybe I've seen that Enrico was there in the and Fabio as well. I don't know if they have a more a better explanation as the one I have. But yes,
I think Marcello, you're right. This is exactly the point. We don't know if we can describe it as zero locus.
Yes, so the claim as I wrote it is wrong, right? So every Fano for the K3 type obtained as a zero of a vector bundle is the same as these examples. Okay. Thank you, Sasha.
There are more